When Alice went through the looking glass, she met the White King. And in one of their conversations, they talked about the performance of Alice's eyes. The king had sent 2 messengers into the town, and he was looking along the road for them. And now Madeline will tell us what he said.
Just look along the road and tell me if you can see either of them. I see nobody on the road, said Alice. I only wish I had such eyes, the king remarked in a fretful tone. To be able to see nobody, and at that distance too. Why, it's as much as I can do to see real people by this light.
Well, of course, we can't actually see nobody, but there must be limitations to what we see. And in fact, there must be limits to what we can feel and smell and hear as well. In this lecture, I'm going to be talking about the limits of our sense organs and whether the limits that are imposed are due to the physical properties of the energy and the substances which are being detected by sense organs, or whether they're because of failures of the biology of the sense organs themselves. Now, let's think about that problem that Alice had. She was trying to see very small things. Now, there's a familiar test that all of you have experienced, I think, that's used for testing how good your vision is. I'm going to prop this up on here and just ask you to indicate which of these lines you can see. Now, how many of you think that you could read the bottom line? Could you put your hands up if you think that you could read the bottom line? Well, there are a few people at the front who think they can. What about the second line? Yes, quite a lot can read the second line. The third line? Yes. The fourth? The fifth? And I think we've got everyone just about now holding their hands up in the room. Now, the visibility of the letters then depends on how big they are, on how close you are. And that depends on the magnification of the images inside your eye. The eye, you see, is an optical instrument. Here's a model of the eye, and you can see that the front of the eye is curved and it's transparent. So it acts as a lens. In fact, the majority of the lens power in the eye is in that front surface, in the cornea. Now, let's see how the eye works using a model. This is a very simplified eye, which contains the 2 main optical components that copy the performance of the eye. Now, if we could have the lights turned down a little, please. The light outside is shining into the curved front surface, which acts like the transparent window in the front of our eye. And then inside is a second lens, just as there is in our own eye, inside the eye. And you can see, if you look at the pattern of rays, which you can see, I think, very clearly on the monitor screens if you can't see it directly, the pattern of rays coming through the eye from that light outside comes curving together, focused by the lens. If I take a screen, like an artificial retina, from the eye and put it into the tank, if I put it into the middle of the eye, you'll see that the rays aren't focused. They form a large circle. But if I move back sufficiently just to the right position, we find a reasonably sharp image of the light outside the eye. Now, that's exactly how the optics of the eye work. The 2 main components of the eye form an image on the back surface of the eye, and that's where the photosensitive cells are. Thank you very much. So let's take apart our model eye and see what's inside. There's that front surface, then layers containing blood vessels, and inside we find that second lens. And actually it's rather clever because it's an adjustable lens for focusing at different distances. And then on the back of the eye itself, inside, That's the retina where the photosensitive cells are, the cells that actually catch the light. Now, in the very center of the eye, you can see it, I think, as a little yellow spot right in the middle of the eye. In that tiny pit, a quarter of a millimeter across, called the fovea, there are 35,000 tightly packed photoreceptive cells called cones. And it's the spacing of those cones, the separation of those cones, which is the main limit to our ability to read letters and to see messengers on the road, in Alice's case. The optics of the eye are remarkably good for a biological optical instrument. It's a terribly good optical system, considering its size. And it's the spacing of those photoreceptor cells, which is the main limitation on our visual acuity. Now, if we look at the first slide, the first picture here, this is an electron micrograph of the retina, which shows the layers of nerve cells and the photoreceptive sensory cells at the back. The retina has been peeled away from the eye. This is the back surface of the eye that we're looking at here. Light has to pass through all the layers of nerve cells before it reaches these rods and cones. And the next picture is a high-power view of the rods and cones. They're thin structures simply packed with photosensitive chemical which absorbs light. Now, those processes that contain the photopigment are amongst the smallest cell processes in the body. Those central cones in the fovea of the eye are only about 1,000th of a millimeter across, just over 1,000th of a millimeter. And that's only twice the wavelength of red light, and it's very, very small for a piece of cellular structure. It's just about as small as it can be. Well, now we can ask a slightly different question, which is, how much light do we need to catch in order to know that we've seen a light at all? Is that process limited by physics or by biology? We know from Newton's ideas and from Einstein's qualifications of them that light comes in irreducible packages of energy called quanta or photons. It's impossible to divide up a photon. Light comes in these tiny packages of energy. Perhaps it's just possible that we can see a light when it contains only one photon of light. If that were the case, then our vision would be limited by physical properties of light, not by biology. Now, to illustrate this question, let me tell you a story. Imagine that the year is 1816, and suddenly, in our sun, in our solar system, a molecule of gas changes its energy state and sends out a photon of light. The photon has a wavelength of about 500 nanometers. That means it lies towards the blue end of Newton's spectrum. This single packet of energy shoots out into space and travels for about 8 or 9 minutes before hitting an object. And the object it hits is a rock on a small planetary structure in our solar system. That structure is the moon. Unfortunately for the quantum, it has a lucky escape because it isn't absorbed by the rock, it's reflected from it. So it goes sailing out into space again, and a few seconds later it begins to enter the atmosphere of another planetary structure, our Earth. And it heads down towards the surface of the Earth into what was then Bohemia, what's now Czechoslovakia, and towards the city of Prague. It strikes an object on the surface of the Earth. And again, it has a miraculous escape, because the object it hits is a blue flower. Now, blue flowers are blue because they reflect blue light and absorb red, yellow, and green light. The colors of objects are determined by what part of sunlight is absorbed by them. So this blue flower reflects the blue quantum of light. So again, after its second lucky escape, it shoots off, and in the twinkling of an eye, it disappears into a black hole. Well, the black hole that it disappears into isn't one of these extraordinary structures in outer space that entertain the cosmologists so much these days. It's a real hole, about 4 millimeters in diameter. It's the pupil of a man's eye. And that man, working in his garden in Bohemia in 1816, is Johannes Evangelista Purkinje, a very famous Czech scientist and anatomist, a great thinker, who was very interested in vision. He was even more interested in gardening. And at the end of the day, as he finished work in the laboratory in his home, he was a medical student at the time, he used to go out into his garden and start working amongst the flowers. He started work when the sun was still up, and worked through until he was working by moonlight. And he made a very strange observation. He found that when the sun was high, he could see the colours of his flowers. He could tell the colours apart, and he saw that the red and the yellow flowers seemed brighter than the blue flowers. But as darkness fell and he was working by the dim moonlight, suddenly he could no longer tell the colours of his flowers apart. They all looked the same colour. But the flowers that he knew to be blue appeared brighter than the ones that he knew to be red and yellow. So there's a strange shift in vision as we go from bright conditions to dark. And that shift now bears Purkinje's name. We call it the Purkinje shift. It involves many things. First of all, we lose our colour vision as we go from light to dark. Secondly, our sensitivity increases enormously by a factor of tens or hundreds of thousands of times. You've all had the experience of walking into a dark room, and at first you can't see anything. But gradually, as time goes on, you begin to see more and more, and see very faint things that you couldn't have imagined that you would have seen when you first entered the room. And finally, the third part of the Purkinje shift, the sensitivity of the eye changes from being most sensitive to yellow and red during daylight to being most sensitive to blue in dim conditions. Let me illustrate why that might be. Now, I've asked the BBC to help me with a little demonstration here, which I think will illustrate this really quite graphically. You see these flowers. Some of them are blue, some yellow, some red. When they're photographed by the television camera, which has, by the way, 3 photosensitive detecting elements, just like our eye in it, one sensitive to blue, one sensitive to green, one sensitive to red. It works very much like our eye. We see all the colours of the objects. And if you look at the flowers, you'll see that the blue ones appear rather dim compared with the very bright yellow one here, or the red ones down there. But now I'm going to ask the BBC in a moment to change to black and white viewing, but in a very special way. They're going to look only at the signals from the blue detector in the camera. They're not going to use normal black and white viewing, but simply take the signal from the blue detector alone. Since the other colours are no longer there, we won't see the pattern in colour. Now, could you do that? Could you switch from colour, please? Watch the yellow flower. You see how dark it becomes. Can we go again to colour? You see, watch the blue flower now. Again, can we go back? You see how bright it becomes. And indeed, look at the handle of the screwdriver that I'm holding. Go back to colour. It's yellow and becomes much brighter as we change to colour. So you see the change in the brightness of the colours as we switch from a 3-detector colour system to a 1-detector blue-sensitive system. And that's exactly what the eye does. What Purkinje had shown was that during the day, we use the cones in our eye, which have 3 different pigments in them. At night, we switch to the rods, which are much more sensitive, but are only sensitive to blue. We only have one kind of photopigment in our rods called rhodopsin. That's the reason that we can't discriminate colours. That rhodopsin is most sensitive at 500 nanometers. That's why blue things appear brighter at night. Well, now then, we can ask the big question. Would it have been possible that that single solitary quantum of light released from the sun, bouncing from the moon, hitting the flower, entering Purkinje's eye, could have made him see? How much light do we need to see? Well, that question has been addressed by 2 different experimental methods which produce much the same answer. The first experiments were done in the 1940s by a man called Hecht, Selig Hecht and his colleagues in the United States. They simply asked human observers to look at a screen on which they flashed spots of blue light of 500 nanometers, the very best wavelength. The observers were in a completely dark room, so they were at their most sensitive. And the experimenters simply found how much light was needed for those observers to say, yes, I can see the flash. And what they found was that under absolutely ideal conditions, a person can see a flash of light of 500 nanometers when only 10 quanta are distributed within 1/10 of a second over a patch of retina containing several thousand rods. Well, what they concluded was that the probability of any one rod absorbing 2 photons was very low, and therefore individual rods must be capable of sending a signal to the brain when they absorb only 1 photon of light. Now that observation, made on the basis of rather a simple experiment on humans, has recently been confirmed with electrical methods, electrophysiological methods, recording directly from the retina. And I've got a remarkable piece of video film made by Trevor Lamb in Cambridge, which shows these experiments. What we're going to see is a recording capillary, a glass tube, placed down in contact with a small dissected piece of the retina of a toad. You'll see the rod cells, and one of them is sucked up into the recording capillary. Can we see the videotape now, please? Now, there's the capillary tube, and the rods below it, and one of them is being sucked up into the tube. Electrical responses can now be recorded through that capillary tube, and we're going to see an oscilloscope screen with a picture of the rod still shown being flashed with very dim flashes of light. In just a moment, the oscilloscope trace is going to show the electrical responses from the rod. Now, there was a tiny flash of light and a little tiny vertical deflection of the beam. Now, a stronger flash, a bigger deflection. And another one, we're going to see several flashes of increasing intensity. And you can see that the response from the rod gets bigger and bigger. Finally, the largest flash of all. Well, those really remarkable experiments, electrical experiments, have shown that a single rod in the toad retina produces a detectable electrical signal when that rod absorbs only one quantum of light. So just as Hecht and his colleagues had concluded from their experiments, rods can produce signals when they receive only the smallest possible packet of energy in which light can be delivered. So there the limitation seems to be one of physics, not of biology. Well, we have to ask the question then, why do we need to see 10 of those quanta roughly simultaneously in order for the brain to accept that it really has seen a flash of light? Well, the brain seems to work a little bit like a democracy. It requires a consensus vote in order for it to accept something. It needs about 10 rods to tell it, yes, I've absorbed a photon, before it agrees that the eye really has seen a flash of light. And the reason is that the receptor molecules themselves, the pigment molecules inside the rods, although they are very stable molecules, they have a half-life of several hundred or even thousands of years. Nevertheless, every now and then, a molecule breaks down spontaneously in just the same way that it would if it actually caught a quantum of light. And of course, those spontaneous breakdowns also produce tiny signals which are sent off towards the brain. Well, if the brain were to accept all of those as being real, we'd be seeing flashes of light all the time that weren't there. This introduces the idea of noise. Noise, unwanted signals, are a limitation in all sense organs to some extent. Let me try and explain what I mean by noise, again with the help of the BBC. We use the term noise to describe unwanted activity, not just in hearing, but also in vision and in electronics as well. And the BBC, despite the fact, as the engineers told me, they've been struggling for 50 years to get rid of noise from television systems and radio systems, they're now very kindly going to put the noise back in for me. They're going to show a picture of me, and I'm going to count, and as I count, they're going to introduce auditory noise and visual noise, and you'll see what happens. 1, 2, 3, 4, 5, 6, 7, 8. Okay, thank you. You see, it became harder and harder to hear me because of the sound that was being added, the unwanted noise, and harder to see my image because of the addition of unwanted, random background activity. Well, there is unwanted activity of physical origin, just these spontaneous breakdowns of molecules of pigments inside the eye, and that basically limits the performance of the brain. Well, now, let's turn from the eye to the ear, and we can ask just the same questions about the ear. What determines the limit of sounds that we can hear? And what's the minimum energy that we can hear under ideal conditions? Is the performance of the ear physically limited, or is it because of a poor quality biological product? Well, let's begin by looking at the structure of the ear. This is a model of the human ear, obviously a much enlarged model, and we can take it apart. You'll see that there's much more to the ear than the bit on the outside, although, as you saw in the first lecture, that's rather important for catching sound and funneling it. And you see that it gets funneled into a long canal through here, and the sound waves, the pressure waves, the vibrating waves, strike a membrane, the eardrum, inside the ear. Then the movements of that membrane produce movements of 3 tiny bones which are locked together, which can move backwards and forwards, the ear ossicles. And those ear ossicles then press on a little window in a coiled up tube, a tiny structure just a few millimeters across, called the cochlea, the snail. And it is a snail-shaped tube full of fluid. And that fluid is being pushed by one of the bones connecting to the tympanic membrane, the outer eardrum. Well, why do we need those bones? If the sound waves came straight in and hit the snail directly, about 97% of the sound energy would be reflected straight back into the air. And that's because the resistance of the fluid inside the tube is very different from the resistance of the air. There's a physical matching problem involved here, a mechanical problem. And that problem is solved by the little set of levers which makes up those ear ossicles. Another reason for having that system is that it ensures that most of the energy that reaches the cochlea actually does come from the outside world on the eardrum. And it protects the ear in a way from sounds being conducted through the bone structure surrounding the ear. Now I'm going to show you a piece of film which shows how those little ear bones work. They really are quite remarkable. They can vibrate at thousands of times a second. Now imagine that one stimulated the ear with sound and set those bones into movement. If they were moving very fast and you took a film of them, obviously all that you would see would be a blur. But if you illuminated with a stroboscopic light the vibrating bones at exactly the same frequency as the vibrations themselves, then the light would catch the vibrating structure in exactly the same position every time. So if we took a film of that, the structure would appear to be completely stationary. If we use a slightly different frequency of stroboscopic illumination, then we can catch the vibrating structure at different positions within its cycle of movement. If we make a film under those conditions, the movement will appear to be very much slowed down. And that's exactly what's been done in this film by Professor Sir Brian Matthews, who was then Professor of Physiology in Cambridge. The film, which we can see now, shows the human ear. This is the eardrum. These are the 3 bones connected together. Here's the third of them pressing into the window of the snail. The movement is produced by a tone of middle C, 256 cycles, and it's illuminated by flashes at about 250 cycles, slightly different. So you can see the remarkable movement of those tiny bone structures. Now then, we have to ask what happens in that coiled up snail, because it's that which contains the sensitive cells. And it's that structure, that beautiful physical instrument, which begins the process of analysing sound. Let's think for a moment about what has to be analysed about sound. Sound consists of 2 properties, intensity and frequency. I can demonstrate the frequency of content of sound to you with this thing. It's an instrument called a spectrograph, and it shows on the screen down here a display related to the sound being picked up by a microphone here. At the moment, it's picking up my voice. Each of these little bars shows the amount of energy present at a particular frequency. The frequency scale runs from about 15 cycles of vibration per second up to 20,000 cycles of vibration. If I take the microphone and hold it in front of a loudspeaker and play through the loudspeaker, if you watch the screen here, you'll see the tones being produced by the loudspeaker. Sweeping through the whole of the frequency range. Now, I wonder if I could ask someone to come. Would you like to come down and help me for a second, please? Yes. Yes, do come. Now, what's your name? David Rosenberg. David Rosenberg. Now, would you like to just hold that for a second and say, when I tell you to, just say, a Merry Christmas and a Happy New Year. Watch the screen.
A Merry Christmas and a Happy New Year.
Okay, and you say it again.
A Merry Christmas and a Happy New Year.
Now, you see the way that, thank you very much. Can you just stay here for a second? You can see the way that the voice contains a wide variety of frequencies, and each different word, each different sound component uses a different part of the frequency spectrum. So when we listen to speech, what we're doing is deciphering the frequency and the amplitude components of the sounds that are coming into our ears. So we have to be able to discriminate frequencies, to analyse them. Now, how can we make a sound analyzer? David here has been practicing with this instrument, an oscillator, and he's going to use it in a moment to try and show you how physical instruments can break down sound. These things, these globes, metal globes, are just filled with air. They were invented by the German physicist Hermann von Helmholtz, and his argument was that large structures should vibrate in sympathy with very deep notes, because the mass of the structure is larger. Tiny structures should vibrate with higher frequency notes. Every object resonates at a particular frequency. An earthquake, for instance, will knock a building down. A building has a very low resonant frequency, but a tiny object will vibrate at very high frequencies. Now let's see if we can make the air inside these balls vibrate and puff out at these little wheels. Can you turn the knobs? See, one of them is beginning to move. Now this one's moving very well. We must have hit the resonant frequency of that one. Now the next one. Now this one's beginning to move. And finally the last one, just starting. That's going at its best. Okay, thank you very much. Thank you, David. So you've seen the way that the physical size of a structure determines what frequency it vibrates at. It turns out that the coiled tube inside the ear acts in some ways as a physical instrument for decoding sound frequency. Now, David's father, Dr. Martin Rosenberg from St. Bartholomew's Hospital, has come to help me today with a demonstration. He's brought with him a very beautiful mechanical model of how that fluid-filled tube works. Now, could you explain it to us?
Well, this is a very simplified model of the cochlea. We've unrolled the snail form of the cochlea, so we have a straight chamber, and this part is filled with water, and there's a diaphragm at one end, and when the plunger moves against this diaphragm, it causes the fluid to be displaced, and the plunger is driven by a vibrator. Now, this is the important thing. In the top of the model, there is a long rubber membrane, just like the membrane in the inner ear, and the essential thing is that it tapers from one end to the other. It's narrow near the plunger end, the middle ear end, and it's wider towards the other end. And this tapering structure gives it its essential frequency selective properties.
Is that true of the human ear as well?
Yes, this is a scale model of the membrane in the human ear. And the first thing we want to see is the very peculiar wave motion that occurs in such a membrane. We produce what are called travelling waves. Now, in order to demonstrate this, we need, again, stroboscopic illumination so we can see the ripples actually travelling away along the membrane. And we recorded this yesterday.
Well, I wonder if we can see the video recording of that. And we should say, of course, that the stroboscopic illumination interferes with the television technique. That's why you can see lines across the screen. It isn't a fault. It's an effect of the stroboscopic illumination. You see the waves heading along the membrane. If you look at the monitors, you can see the waves travelling along the membrane. They're travelling very much more quickly than you see them because of the stroboscopic illumination. And they produce maximum vibration in one particular place on the membrane.
Now, the important thing about this membrane is it acts as a frequency analyzer. And we can't see this very clearly in the stroboscopic picture, but if we put a thin layer of water on top, we can see where the maximum vibrations occur for different frequencies. And this is some green water, just to make it look attractive. And now, if we feed into this a frequency of 50 hertz, we make the vibrator work at 50 hertz, we see that the membrane is vibrating, and we'll see that it's vibrating at the widest end of the membrane.
So you can see the vibrations quite clearly about here.
Now we'll increase the frequency to 100 hertz, 100 cycles a second, and we should see the vibrations occurring there in the middle of the membrane. Now we'll increase the frequency still further to about 150 hertz, and now we can see that the vibrations are towards the other end. And once more, 200 hertz. And now they're right at the other end. So here we have the basis for analysing a complex sound, a normal sound, into its component frequencies.
But isn't it true that presumably the amplitude of vibration depends on the intensity of the sound? Could you just turn that sound up and see what happens?
Yes, let's go down to a lower frequency.
Thank you very much. Well, you can see then the way that the mechanical structure of the ear, the way that it begins the process of analysing intensity and frequency without any intervention from the nervous system at all yet. But of course, at some point, messages must actually be sent to the brain. Now that depends on sensitive cells that are scattered along that membrane inside the human ear. Imagine we cut a section of that tube, that fluid-filled tube, in the human ear and had a look at it. It would look like this, the next picture. This is the membrane, the vibrating membrane, which goes up and down. There's fluid underneath, and actually there's fluid above as well. And resting on the membrane are specialized, very sensitive cells connected to nerve fibers with tiny hairs that stick out into this solid structure above them. Now imagine if the membrane bounces up and down, those hairs are going to be moved backwards and forwards. The next picture shows a very high power scanning electron micrograph of a top view of those single cells. And here are all the rows of hairs that stick up, implanted into that solid structure. It's movement, vibration of those hairs, which sets up signals in the nerves that go to the brain. Now, as we've seen in the model, the range of frequencies that can be handled depends on its physical structure. So our ear is limited to a certain band of frequencies. I'd like to demonstrate to you what that band of frequencies is. I'd like you to listen to the sounds again that are produced by the loudspeaker. And once again, I'm going to run through the whole frequency spectrum. And I'd like you all to listen very carefully for the tone and to put up your hand when you can hear it. So if everybody could keep very quiet, listen to the tone. I'll shout out the frequencies that we're listening to, and I want you to try and put up your hand just when you're quite sure that you can hear the noise. Well, that's 10 cycles a second. Nobody's hearing it. 15, 20. Few people beginning to put their hands up now, yes, towards the front. 20 cycles, obviously it's more intense at the front than at the back. Keep your hand up as long as you can hear it, please. 25, 30, almost everyone now is hearing it. 40. Okay, well, we'll go quickly then through the middle band where we're most sensitive. 400, 1,000, 2,000. Now, this is the region that's loudest. That's where we're most sensitive. Now, keep your hands up as long as you can hear it, please. Well, some of the hands are beginning to go down and say, Bill, you're right at the front and your hand's gone down. 12,000. Well, it looks as though the adult hands are going down when the children's hands are still up. I think what I'm measuring is not just your hearing, but also your age. We're now up to about 16,000 cycles, and a lot of the children have still got their hands up. I can't hear this at all, and I'm right next to the speaker. 17, 19. Okay, everybody's down at 20. Right. I'm sorry to say that past the age of about 20, you lose about 1 cycle per second every day of your life from your auditory sensitivity curve. We gradually lose the ability to hear very high frequencies. Well, I think that's an interesting prelude to the next lecture, which is going to be about the limitations of our sensory systems and the possibility that other animals might see and hear and smell and taste things that we don't know about. And I'd like to prove to you, as an introduction to that lecture, that it really is true in the case of hearing. Now, could I have the next guest, please? Sally Johnson? Yes. Now, this is Sally Johnson and Fresca. I wonder if you could get Fresca just to sit down in the front, please, for a moment. Now, the hearing of dogs is very good, as we all know, and I'd like to prove that to you if you all listen extremely carefully to what I'm going to do now. If you just watch Fresca, could you call him towards you? Yeah. That's right. Okay. I think it's fairly convincing that the dog is hearing this. Well, this, if you'd like, all like to listen, is completely inaudible. This is a model bat, which I'm going to use in my next lecture. It emits, thank you very much, it emits sound of it emits sound of 40,000 cycles a second, twice as high as any of us in this room were able to hear, but Fresca can hear it. Now, I'd also like to use Fresca for another demonstration, because I want to move now from hearing to smell, to the chemical senses, smell and taste. We tend to, perhaps, to neglect or to underrate our ability to smell and taste things. Obviously, vision and hearing are really rather more important to most of us than the sense of taste and smell. But to a dog, smell and taste are pretty important. And the powers of discrimination are really quite extraordinary. Now, I'd like to try and prove that to you. Now, I have here a T-shirt which came from a member of the audience who wore the T-shirt yesterday. It wasn't washed, wore it just for one day, and brought it along today. And we hope that Fresca is going to help us to find that child in the audience. Can you? Okay, is that enough, do you think?
Yes, I think so.
Okay, well, let's see.
Good girl.
We've found somebody, apparently, yes?
so.
Could you come down? Can I ask your name? Shireen, this is Shireen. And is this your T-shirt? No. No? It's not yours. Fresca, you've made a mistake. Can you try again, yes? All right. Could you come down?
Yeah, she says it is. Come on, good girl.
Well, now, what's your name?
Serena.
Zarina. Is this yours?
Yes.
It is. Thank goodness for that. Would you like to take it? Well, now, just come and turn around. There's a certain similarity here between these two. They're identical twins, and it's not surprising that Fresca made a mistake. You see, we all smell. We all have our own individual smells, and those smells are determined genetically. They're determined by our physical structure. And these two are so similar that the smells that Fresca was using to identify them are probably virtually identical. Thank you very much. Thank you. Well, we've seen an example of the power of smell in an animal, and now we have to ask that same question again that I've already answered for hearing and for vision. How much do we need in order to be able to smell? What's the minimum amount of smell? Now, smell obviously depends on chemicals, on molecules, on substances that we take into our nose or that we taste on our tongue. We can ask the question then, how many molecules, how much substance do we need in order to be able to smell or taste something? Now, for the human senses of taste and smell, probably the answer is that we need a fair concentration of everything except the things to which we are most sensitive. Many animals have smell as their dominant sense. There are animals that are virtually blind, many of the invertebrates, the insects for instance, some of them are virtually blind. They can't hear, they have no ears, they have sensation on their skin, but most important, they have smell. Their smell organs are usually in their antennae on their head, as well as around their mouth and perhaps sometimes on their legs. The most sensitive ones are in their antennae. And they use these things to talk to each other, to communicate with each other. Just as we look at each other, make facial expressions, and talk, many insects use smell to talk to each other. They produce a variety, many different sorts of secretions from their body, which are quite characteristic in their signal that they send to other animals of the same species or different species. They can communicate their physical state. They can say whether they're well or happy or not. They can communicate what sex they are, male communicating to female or vice versa. They can tell whether they've been injured in a particular place, for instance. There are a variety of different things that animals can tell to each other through their chemical senses. So their senses have to be, their chemical senses have to be very sensitive. Well, I'd like now to show you a remarkable piece of film, an extraordinary piece of film, of one of the most sensitive reactions of a chemical system known in the animal world. This comes from a film made by Karl Keisling in Germany of the reactions of a certain sort of moth. And what we'll see in the film, if we can start it now, please, if you watch the monitors, we can see a group of male moths reacting to a female. Here's the female. She's been sealed up in a glass container, completely sealed with Vaseline to stop any movement of air from her outside. And there are a group of 3 male moths inside a tank, and a fan's going to be turned on to blow the air from the male towards the female, not the other way around to begin with. There are the males on the left. Now, the lid's being lifted. There's absolutely no reaction from the male. If they could see her, they would see her. If they could hear her, they would hear her, but they don't. There's no reaction. Now, she's covered again, and you'll see that the fan is turned around to the other side of the chamber. Now it's turned on again. And the cover's lifted, and watch the reaction. Instantly, the males detect the presence of the female using their antennae. Their wing fluttering is a characteristic reaction, and they move towards the female. Well, I think perhaps we better stop the film at that point. Well, it turns out that moths of that general variety are so sensitive to the smell of the opposite sex, the male to the female, that they can detect her at up to several kilometers away under ideal conditions. And probably they can respond at a concentration of that smelling material called a pheromone of only about 40 molecules per cubic centimeter. Electrical experiments involving recording from the antenna, if I could see the next picture, please. This shows a tiny section of one of the side branches of an antenna. The scale at the bottom is just 1/10 of a millimeter, to give you an idea of how big they are. These are the individual little smelling hairs that stick out. It's possible to record electrically from them. Using that technique, it's found that the absorption of one molecule of that pheromone substance can cause a single nerve impulse. So again, the system seems to be as sensitive as it can be. You can't have less than one molecule of a substance. So again, it's physics, not biology, that ultimately limits the sensitivity of the system. Now then, what about taste? Human beings have smell, they have taste, they have special receptors on their tongue. And the next picture shows a tongue. This is the tongue of a 5-year-old little American boy who's just taken a lick of vanilla ice cream. Now, amongst the white ice cream, you can see these little red dots. Those are papillae, little bulges on the surface of the tongue. The next picture shows a high-power cross-section of 3 papillae. And you can see that on the sides of the papillae are these things, which are called taste buds. And they're filled with sensitive cells, sensory cells, with little hairs, rather like the antennal hairs, sticking out to taste the fluid on the surface of the tongue. It's those hairs that have on them the specific mechanism for detecting and analysing molecules reaching them. Each receptor responds particularly and specifically to a particular thing. Well now, we're said to have 4 different sorts of taste: salt, bitter, sweet, and sour. That must mean we have 4 different sorts of detector molecules on those hairs in our tongue. And I'd like to try and show you a demonstration of that. Can I have the 4 people who said they were going to help a little earlier, please? Could you just come down and put, each of you come to the front and put a blindfold on, please? Yes, and 2 more. Could you just go down to stand out at the front of the bench, please? Yes, take that and put it on when you get down there. Okay, just go and stand out at the front. Good. Now, could you all move along just a little, please? Just move along. That's very good. That everyone can see you. Just face forward. Excellent. You can't see anything, can you? Make sure you can't see. Now, I'm going to give you some nice, fresh fruit to taste. And I'd like you to tell me what you think of it. I'm going to give each of you a piece of fruit. I'd just like you to take a nice, good bite and a suck. Here you are. Here's yours. Can you hold your hand out? Whoops, don't drop it. Now, what do you think of that?
Sour.
It's sour, yes. What do you think?
Sour.
What is it, do you think?
Lemon.
You think it's a lemon. What are yours? What do you think it
It's
is?
quite sweet.
Yes, and what is it, do you think?
Sugary.
It's sugary, yes. What do you think?
Sweet.
Yes, and
think it's a
what do you think it is?
No.
You don't know what it is. Yours is,
A lemon.
you think yours is a lemon. Could you take the blindfolds off, please? Well, you're all eating lemon. Do you want to put them back on the plate? Now, you two, this is a nice trick. The two in the middle here were kind enough to chew on a little tablet of freeze-dried fruit, a very special fruit called miracle fruit. I'll explain to you what it does in a moment. Thank you very much indeed. The next picture shows miracle fruit. It comes from West Africa. They're a very small fruit, the size of an olive. They taste quite sweet themselves, but they contain a remarkable substance. This substance seems to attach specifically to the sweet receptive structures on the taste buds. And every time something sour comes along, it stimulates the sweet receptor. So very sour fruit tastes very sweet. In fact, almost everything tastes terribly sweet and will do for about 2 or 3 hours, I'm afraid. Well, I said that most of us underestimate our sense of taste and smell. We don't use it that much, but there are some people for whom taste and smell is really terribly important. And they show us how excellent those senses can be if we choose to use them properly. Now, my next visitor is Michael Broadbent, and I wonder if he'd come down, please, to help us. Michael, I wonder if you could tell us what you do.
Oh, I taste and auction rare wines at Christie's.
At Christie's? Well, I think you're being rather modest. Michael's one of the best-known wine masters in this country and has written a small book which is virtually the Bible of wine tasting, which tells you how to do it. I suspect that it doesn't mean that everybody's able to be as good as you are. I wonder if you can help us, Michael, to try and identify 2 wines. And I can assure you that Michael has not seen these wines before. He doesn't know what they are. We'll start with the first one. Is that about the right amount?
Mm-hmm, that's fine.
Oh, you're looking at it. Is that
Yes.
important?
Yes, it is. Yes, particularly with red wines.
Yes. And now smelling it, that's...
Smelling is very important, certainly for the professional. Very pleasant, probably Bordeaux.
Yes.
Nice and fruity, certain amount of tannin and acidity. It's about 6 years old, possibly.
Yes.
Nice to drink now, it'll keep for a little while. Very pleasant. Very nice
Any
quality.
idea of the district?
I just thought it was in the Medoc of Bordeaux, smack in the middle. I really don't know the name of the chateau. Something like Giscard, or something, a moderately good chateau.
All right. Can we show you what it is? It's a Bordeaux. It's 1975, 7 years old.
Wrong side of the river.
It's the wrong side of the river, but very, very close. Excellent. All right. Now the second one.
Not this strange artificial colour. It's slightly more purple, rather lighter. Well, it's different. It's younger. It's perfectly straightforward. More like fruit juice than grape juice. Certainly not Bordeaux. Certainly not a classic wine. Not from one of the classic districts. Present young and fruity, made what we know as the whole fruit method, maceration carbonique. I just don't know what it is exactly.
Does the colour help you at all?
The colour, the slightly pink tinge reminds me of a young Beaujolais, but in fact it isn't quite that style.
Not a classic wine, then?
No.
Would you say that Chablis is a classic wine?
Oh, this is Rome Chablis.
I'm sorry to say that we fooled you. This is a white wine, a Chablis, a very great wine, which we've put a colour in, and the colour was made to match Beaujolais, which is exactly what you said. We did this deliberately, I should say, because I wanted to try and show the importance of colour in determining the total judgment of taste, as you yourself mentioned
yes.
in your book. Do you think it's a fair test of that?
I think absolutely.
Thank you very much indeed. Thank you. Now then, let's turn from smell, hearing and vision to touch, the last of the major senses. Touch is much more than just detecting pressure on the skin, as we'll see in later lectures. We can detect temperature and pain and so on with our skin as well as touch. But under ideal conditions, you know, we can detect vibration of our skin, touch of our skin, with an amplitude of about 1/2 of 1,000th of a millimetre. So again, the receptors are really just about as sensitive as one could imagine they could be. We're also very good at detecting the separation and the shape and the texture of objects with our skin, especially with our fingers. That's the whole basis, for instance, of Braille reading, recognizing texture with the fingers. I'd like to ask for a volunteer from the audience. Would you like to come and help me? Would you like to sit down at the front and put on a blindfold? And I'm going to test, can I ask your name?
David.
I'm going to test David's sense of touch using a classical neurological instrument. Actually, this was made at the beginning of this century. It's still used by neurologists now to test the discrimination of the skin. Now, I'd like you to tell me, I'm going to touch your fingers with either 2 points, like this. That's 2, all right? You can feel 2, or 1. And I want you to tell me whether it's 2 or 1. Just say 2 or 1 each time.
2. 2. 2. 1.
Thank you. About a millimetre separation. Now, if you could roll up your sleeve, that's probably good enough.
2. 2.
Well, we need to go a little bit higher. Could we undo a button? Thank you. All the way up. That's excellent. Very good.
1. 1. 2.
Okay. 2, and the separation in that case was more like 4.5 centimetres. 40 times change in sensitivity on going up the arm. The reason for this is because the tips of the fingers have a very, very rich supply of nerves. So we're able to tell the positions of things on the fingers very much better than we can high on the arm, where there are fewer nerves. Just like the fovea of the eye, there are many, many nerves packed into a tiny area there, but not so many here. Okay, thank you very much, David. Well, finally, let's turn from the sense organs, all of which seem to be limited by physics, really, rather than by poor quality biology, to the final step, the transfer of information from the sense organ to the brain. And that, I'm afraid, is where biology has its problems. You see, however good biology has been at designing detector mechanisms, instruments of detection, it hasn't done terribly well on designing cables. Unlike the cables that are used for telephones, for instance, nerve fibres are rather poor quality conductors. Biology hasn't been very good at making insulators to cover the cables with, or to make really fine conductors for the signals to go along. So nerves have to signal, not like certain cables do, by sending a voltage simply from one end to the other, and signaling information by the magnitude of that voltage, by variations in the voltage. Nerves have had to resort to a trick of digital coding, frequency coding. Nerves transmit pulses, and the pulses are always the same size. They travel rather slowly along the nerve, and the signal, coded by the sense organ, according to a voltage that it produces, is converted into a stream of impulses, where the impulses represent the intensity of the stimulus. I'd like to try and demonstrate nerve impulses to you with a very simple preparation, in which I'm going to record from a single fibre, nerve fibre, in a worm. Now, John, could you help me, please? There is a worm in here, isn't there? We've got a worm in here which has had a very merry Christmas. It's just been soaked in 10% alcohol, about the strength of wine, for a few minutes, just to make it very drowsy and anaesthetised. And we're going to rest the worm across some electrodes. Now, the first pair of electrodes, these, can be used to deliver a very tiny electric shock to the single big ventral nerve cord, which contains one giant fibre in the worm. So an impulse should travel along to these recording electrodes at the other end. Now, if we use a small enough shock, all that you'll see recorded from the recording electrodes is instantaneously the current that spreads along the nerve. You'll see a little tiny signal at the beginning of the trace on the oscilloscope. But if the shock is strong enough, we'll see it followed sometime later by a true nerve impulse travelling much more slowly. Now, can you look at the monitors up there, which are watching the oscilloscope screen, while I turn up the intensity of the shock. There at the beginning of the trace, if you look carefully, you can see the recording at the top of the signals from the nerve, and nothing's happening except that first shock artifact. I'm turning up higher, and we should see a nerve impulse. There's the nerve impulse, that second component. You see it suddenly appeared. It's not changing in size as I increase the strength more. Now, as I go down, it should suddenly fail. There, it's gone. The threshold is about 4 volts. It's back again now. John, could you just measure on the screen the delay, please, between the two? Now, we saw that it took a considerable time for the nerve impulse to arrive. About how long? 5.8 milliseconds for a distance of about 6.5 centimetres. That means it's being conducted at just under 1 metre per second, really rather slow. Actually, that's very much slower than most of the nerves in the human body. But still, we have significantly slow delays in the conduction of the fibres. Now, another big problem, apart from the delay, is that nerves can't transmit many impulses. Now, if you can look at the screens again, I'm now going to switch 2 pulses on and give 2 shocks, one after the other, with 1 millisecond delay between them. If you watch, you can see 2 shocks at the beginning of the trace, but only 1 impulse. I'm going to make the second shock come at a longer and longer time after the first. It's 2 milliseconds now. Still only 1 nerve impulse. 3 milliseconds. Still only 1. But if I go to 4 milliseconds, you see the second nerve impulse right at the end of the trace. So the second shock is only able to produce a nerve impulse if it occurs 4 milliseconds after the first. If we go back to 3, it disappears. So you can see that this particular nerve is only able to transmit impulses at a spacing of about 4 milliseconds. That means a maximum frequency of about 250 a second. It's a really very poor signaling machine. And that limitation, the property of nerve fibres, is the thing that restricts, ultimately, the performance of our sense organs. I won't say that biology has failed. It can't make perfect conductors, but it has managed by a variety of tricks to overcome their poor properties. Let me simply finish by reintroducing our bionic head. Now, you'll remember that he has ears, he also has eyes. Could you reduce the intensity of the light, please, in the room? Could you reduce the light intensity, please? You can listen to the nerve impulses that his eye is producing. Okay, can we stop there? If I shine a light into his eye, you can see the signal from the eye on the lower trace of the oscilloscope, and the nerve impulse is produced by it on the upper one. The problem is that it can only work over a small range. If I bring the light close enough, the photo cell will still respond, the eye will respond, but the nerve impulse will stop. It can't go any higher than that frequency. Now, that's a basic problem that has yet to be overcome, and I'll tell you how it's done in my 5th lecture.